The objective is strictly defined. Aviation archaeologists and institutional recovery teams evaluate isolated crash sites to determine the physical feasibility of removing intact historical airframes. The constraints dictating success or failure are not determined by the desire to preserve hardware, but by the geometry of the terrain holding it. This is the case of the Douglas B-18 Bolo, serial number 36446. On February 25, 1941, this twin-engine medium bomber went down in the Kohala Mountains on the Big Island of Hawaii. It remains there today. The aircraft rests at an elevation of 3,500 feet. The primary airframe is largely intact, sitting on a steep, forested slope. The physical boundary preventing easy retrieval is immediate, but its exact dimensions are not securely documented. Contemporary accounts place the bomber in a gulch after it struck trees and skidded about 75 yards. A later property owner stated that the wreck subsequently slid farther into the gulch. The terrain remains steep, wet, and severely restrictive, but no reliable survey located for this review confirms a vertical drop of exactly 75 feet or proves that conventional staging is categorically impossible. Investigators approach a site like this not to immediately extract the wreckage, but to map the boundaries of what is possible. The primary objective is to assess the remaining bulk structure for potential museum recovery. Before any lifting plan can be drafted, engineers must verify the stability of the resting position. A visual inspection confirms the aircraft did not shatter against a rock face. The fuselage, wings, and tail section remain coherently linked. This level of preservation is highly unusual for an aviation accident in mountainous terrain. Typically, a controlled flight into terrain at this elevation results in fragmented debris fields spread across wide impact zones. Even so, early accounts describe the aircraft coming to rest in a gulch after a short but measurable skid through trees and undergrowth. Its exact original attitude is not preserved with survey precision. Later testimony from the property owner states that the wreck eventually slid farther into the gulch, meaning its present position cannot be treated as an unchanged record of the final seconds of the crash. The Douglas B-18 Bolo was a foundational military aircraft, making serial number 36446 a highly valuable asset for aviation historians. When assessing a site with this level of historical value, the initial phase requires establishing a physical baseline. Teams would first need to document the current orientation of the fuselage within the gulch. Steep ground, dense vegetation, wet soil, and the possibility of further movement could restrict inspection of the forward structure. The available historical record does not establish a single safe approach route. Any access boundary would require a current professional assessment conducted with the landowner's permission. This geographic limitation means that mapping the complete structural condition requires specialized anchoring simply to inspect the forward fuselage. The operational constraint is rigid. You cannot build a support cradle under a bomber that is suspended over a 75-foot gap. The investigation team must work entirely from the uphill slope, fighting the same steep gradient that holds the bomber in place. The resting geometry remains unforgiving, even where its exact dimensions are unverified. This leaves the investigation with a bounded question. How did a largely intact medium bomber come to rest in the gulch? The decision to divert an aircraft on a single engine forces an immediate penalty in aerodynamic drag. At 10,000 feet, thrust becomes a strict currency. The Douglas B-18 Bolo was a heavy medium bomber, and losing half of its available power fundamentally altered its flight envelope. The left engine suffered a catastrophic main bearing failure. Thrust on the port side dropped to zero immediately. The pilot initiated a diversion toward a secondary landing field, relying entirely on single-engine power. This action triggered a severe operational trade-off. To keep the bomber flying straight with asymmetrical thrust, the pilot had to apply heavy, constant rudder input to counteract the pulling force of the remaining good engine. The crew also had to reduce drag and hold the most effective available airspeed. Those actions could improve single-engine performance, but they could not create power the aircraft did not possess. According to Hubbard's official account, the bomber remained too heavily loaded to maintain altitude, even after fuel and cargo were jettisoned. The crew therefore held altitude as long as possible before the aircraft continued descending. The bomber entered a slow, continuous descent. The crew was operating in total darkness during an instrument navigation training flight. The unexpected loss of airspeed and the constant fight for directional control disrupted their navigational awareness. Published accounts state that, without outside visual references, the crew believed they were still over the ocean. Whether they experienced physiological spatial disorientation cannot be confirmed. What is documented is that the mountain appeared without warning while the bomber was still descending in instrument conditions. The pilot was forced into a split-second decision gate. The remaining engine lacked the necessary thrust to climb over the sudden terrain. A level flight path would drive the nose directly into the rising rock face, ensuring complete destruction. When the mountain appeared, Hubbard later recalled that he pulled back hard on the control wheel. The abrupt pitch change increased the angle of attack, and the aircraft stalled as it entered the trees. The surviving accounts do not record the exact control position, airspeed, or angle of attack at that moment. As the wings exceeded their critical angle of attack, lift decreased sharply and drag increased. The stall did not eliminate all lift or erase the bomber's forward motion. The aircraft continued into the vegetation, contacting the tops of trees before skidding through dense undergrowth. That combination of reduced airspeed, vegetation, and ground contact probably dissipated much of the remaining energy. Whether any other response remained possible in those final seconds cannot be established. Hubbard's pull-up was an instinctive emergency reaction to terrain appearing directly ahead, not a controlled or repeatable vertical drop maneuver. The exact load sequence through the wings, fuselage, and crew compartment was never instrumented and cannot be reconstructed from appearance alone. What the surviving accounts establish is that the aircraft remained sufficiently intact for all 6 men to survive. The bomber reportedly skidded about 75 yards through dense undergrowth before stopping in the gulch, leaving an isolated resting place that created a formidable rescue and salvage problem. All 6 crew members survived. Search aircraft located the wreck the following morning and dropped supplies to the men. At dawn on February 27th, a rescue party approached by horseback and then cut a trail for 8 miles through marshland and heavy brush. Published accounts differ on the exact duration. One reconstruction places the rescuers at the wreck around noon that day, while Hubbard's official Air Force biography gives approximately 1.5 days to reach the crew and another 1.5 days to get out. The precise rescue timeline therefore remains disputed. Hubbard and at least some of the other crew members sustained minor injuries. The Kohala summit area presented rescuers with steep ground, marshland, heavy brush, and saturated terrain. These conditions made ordinary vehicle access exceptionally difficult, although no geotechnical survey has been located that proves every wheeled or tracked system would fail. That human route was not automatically suitable for moving an aircraft. Moving a multi-ton aluminum aircraft structure out of the same environment requires an entirely different operational scale. Standard aircraft recovery over land depends on establishing a heavy transport corridor. To move a medium bomber, engineering teams must clear a wide path, stabilize the ground surface, and deploy heavy machinery such as bulldozers, flatbed sleds, and lifting cranes. The saturated ground presents a major obstacle to meeting those logistical requirements. Furthermore, the severe incline of the mountain slope prevents the safe operation of heavy lifting gear. Industrial cranes and winches require a flat, solid base to distribute weight and prevent tipping under load. The steep gradient surrounding the wreck may leave little usable space for staging. If engineers attempted to drag the fuselage intact, the deep mud would create massive friction against the lower hull. Dragging the airframe uphill through this dense medium would exceed the pulling capacity of portable, tree-mounted winches. The immense drag forces would also tear the thin aluminum skin and underlying bulkheads apart long before the aircraft reached flat ground. Disassembling the aircraft into smaller, human-portable sections requires heavy cutting equipment. Industrial saws and torches demand portable generators, bulk fuel supplies, and heavy support gear. Transporting large cutting, lifting, or hauling equipment into the area would have presented major logistical difficulties. The available records establish that rescuers removed the bomb site and flight instruments, and that the damaged bomber was then abandoned because of its remote location. No formal 1941 engineering study, road cost calculation, or institutional salvage report was located for this review. The exact decision process therefore remains unconfirmed, even though the practical difficulty of conventional recovery is clear. The 1941 abandonment did not establish a permanent technological limit on every later survey. Any modern operation would still be constrained by private property, steep wet terrain, vegetation, aircraft condition, environmental requirements, and the safe movement of equipment. Human portable cameras, survey targets, measuring equipment, and battery-powered instruments would be among the simplest tools to bring by ground. Heavier equipment might require separate aerial or engineered logistics, subject to permission, and a site-specific safety assessment. Ground removal of the main structure has never been demonstrated as practical, but the historical record does not prove that every modern alternative is physically impossible. The site geometry restricts access to portions of the largely connected airframe and limits what can be measured from safe positions. The structural condition preserves part of the mechanical record, but the exact impact attitude, deformation sequence, and distribution of loads cannot be established without a documented debris map and structural analysis. Later sliding, corrosion, vegetation growth, and the removal of components have further altered the evidence. The known performance limit comes from the flight account, not from the present shape of the wreck. The surviving airframe records the outcome of the emergency, but it cannot independently measure the available thrust, aircraft weight, propeller condition, or climb capability. Using the surviving evidence would require strict limits on physical interaction. Steep ground, vegetation, unstable soil, later movement, and weakened structure could make portions of the nose, cockpit, and lower fuselage difficult or dangerous to inspect. Restricted sightlines and inaccessible surfaces would limit the completeness of any site survey. Photogrammetry does not require a physical baseline running across the entire length of an artifact. Scale and position can be established through suitably distributed control points, known dimensions, surveyed camera positions, or other geospatial control. Occluded sections could remain incomplete or less accurate, but accessible portions of the wreck could still be modeled. The exact control network would depend on the geometry and safety conditions found at the site. Where direct physical access to the forward lower fuselage is unsafe or unavailable, surveyors could not assess specific damage to the forward bulkheads or lower structural ties, conduct intrusive sampling, or document hidden components in detail. Any attempt to push, shift, or lift the structure for inspection could destabilize weakened sections or the surrounding ground. Survey design must therefore prioritize non-contact optical mapping from positions established as safe. The bulk airframe holds the story, but high-value components required a different extraction logic. Decades after the crash, selected components were removed from the Douglas B-18 Bolo, while the main airframe remained in the gulch. Sources report the removal of internal fittings, the retractable top turret, and the nose cone, but the full chain of custody is unclear. One account associates components with work on a United States Air Force Museum B-18A, while a specialist aircraft directory lists the top turret at the Pima Museum. The evidence does not securely establish a formal Air Force decision to extract both a nose turret and a dorsal turret for two specified mainland restorations. The detailed method used to remove the surviving components is poorly documented. No operation report located for this review identifies the personnel, tools, cutting sequence, rigging material, center of gravity calculations, aircraft type, or rotor downwash effects. Environmental exposure and corrosion would have made any removal delicate, but the exact procedure remains unconfirmed. Without photographs, load records, or participant testimony, the operation cannot responsibly be reconstructed step by step. The incomplete record of component removal does not establish whether the same method could or could not be scaled to the main airframe. A whole aircraft recovery would require a separate assessment of weight, structural strength, attachment points, terrain restraint, flight conditions, and legal authority. Detached components would present a fundamentally different load from the connected wreck. However, the present mass of the stripped airframe has not been measured, and helicopter external load capability varies by aircraft, altitude, temperature, fuel state, and operating profile. Rotor downwash and dynamic loading could threaten weakened metal or unstable ground, but those effects have not been quantified at this site. No comparison with a specific aircraft can be made until both the recoverable load and the operating conditions are known. The fuselage appears to have settled into wet ground and vegetation, creating resistance beyond the remaining weight of the aircraft itself. The magnitude of soil adhesion, root entanglement, and residual structural strength has not been measured. A concentrated lifting load could cause severe deformation or breakup before the wreck was released, but the precise failure mode cannot be predicted without inspection and engineering analysis. Breaking the fuselage into smaller sections would be destructive and would introduce major logistical, conservation, and structural risks. Heavy corrosion could cause adjoining skin and ribs to fail during cutting or handling. For the present, the main shell remains exposed to continued environmental deterioration. The terrain remains a continuing threat to the surviving structure. The property owner reported that the aircraft eventually slid from its original position into the gulch. Gravity, rainfall, saturated soil, erosion, and vegetation may all have contributed to that movement. However, no monitoring record located for this review measures an annual rate of displacement or proves that the wreck moves during every wet season. The timing and precise mechanical cause of its movement, therefore, remain unconfirmed. Any continued movement would impose new loads on an airframe already exposed to more than 8 decades of moisture and vegetation. Significant corrosion and loss of section are plausible, but the remaining tensile strength of the skin, frames, and bulkheads has not been measured. Photographs can document deterioration, but they cannot, by themselves, establish the current internal load paths or prove that the fuselage is steadily buckling in a particular direction. The precise structural condition remains unconfirmed. The current management and recovery status of the wreck is not fully documented. Recovery has reportedly been discussed over the years. In 2007, a property owner stated that a possible recovery was being considered in cooperation with what was then the Pacific Aviation Museum. However, a later museum curator stated that the aircraft was not the museum's property. No formal museum engineering survey or comprehensive extraction plan was located for this review. No public record located for this review identifies multiple active proposals, a formal indefinite deferral, or a diagnosis of terminal material decay. The wreck's remoteness, uncertain structural condition, difficult terrain, private ownership, and potential conservation risks all complicate intervention. These factors may explain why no comprehensive recovery has occurred, but the precise reasons for institutional inaction remain unconfirmed. It also cannot be assumed that every possible stabilization attempt would accelerate destruction. Stabilizing the wreck would require a site-specific structural and geotechnical design. Ground anchors, cables, cradles, straps, or other supports could introduce vibration, concentrated loads, and disturbance to unstable soil or weakened metal. Those risks are serious, but their magnitude cannot be predicted without measurements of the slope, soil, airframe strength, and possible attachment locations. No evidence located for this review proves that anchors would inevitably collapse the ravine edge, that support netting would necessarily crush the fuselage, or that every engineering solution would fail. The wreck may now be too fragile for casual intervention, but neither a precise equilibrium nor an immediate failure threshold has been demonstrated. Non-interference may be the most cautious temporary approach unless a professional survey supports another course, but it cannot be declared the only physically viable option. The main airframe remains unrecovered, and no documented permanent deferral or formal observation-only management plan was located for this review. Any future decision would depend on the landowner, relevant authorities, conservation objectives, and a current technical assessment. Access remains subject to landowner permission, safety considerations, and any applicable legal or environmental requirements. Photography and non-contact documentation may be appropriate, but no published program was found that restricts future visits exclusively to monitoring structural decay. Repeated surveys tied to a stable geospatial control network could map changes in the wreck's position, photograph developing fractures, and measure deformation over time. The airframe endures in the gulch, its future governed by terrain, corrosion, weather, and the limits of what can responsibly be documented or preserved.